Okay, so now our second task is to figure out whether we crash or not. So essentially, if you look at our workspace, right, we have the delta V's and we have the T's. Okay, so for example, our first sample, my delta V is 239-ish, my T is 55-ish. For this pair of samples, how do I figure out whether I crash or not? So let's open a function called crashed. It's going to be returning true or false. And my arguments for this is going to be include delta V and T. Okay. I'm going to be returning this result. All right. So mathematically, how do we figure that out? So we know that initially we have 10 km to spare, and we want to figure out, does it take that much space for us to decelerate to 0 or not? So this is time, this is velocity. We started with 250, and we know we have 2 legs of deceleration. The first leg is a fast deceleration, right? It happens over an interval of t, and we decelerate to 250 minus delta v. So the area below this trapezoid is the distance covered during the first leg of this deceleration. The second leg of the deceleration is a triangle. The rate of deceleration is much smaller because we are using a much weaker thruster. But the length of the deceleration is going to be the leftover velocity divided by the rate of this deceleration, which is 0.01. So the length it takes over here, this entire interval, is going to be 250 minus delta v. That's the leftover velocity divided by 0.01. So that's going to be the length. And if we multiply the length by the leftover velocity, we're going to get what? We're going to get the distance covered, right? Divided by 2. So that's the triangular area. So let's figure out the first leg is going to be equal to the area of the trapezoid, which is T times 250 plus 250 minus delta V divided by 2, right? So that's the area of the trapezoid. Okay, second leg is going to be the area of the triangle, which is going to be 250 minus delta V. Okay, that's the height of the triangle times the base of the triangle, which is another 250 minus delta V, then divided by 0.01. So let's just square that and divide by 0.01, divide by 2. All right. So result is going to be equal to whether first leg plus second leg are greater than 10 kilometers or not. If it's greater, then we would be crashing into the asteroid. So that's basically a function that determines the outcome of the simulation. Right? In a lot of cases, the simulation given a sample has to be the solution of an ODE or PDE, right? But in this example, we have such a simple problem, we can figure out the result analytically. Okay, so now the third part is going to be computing the probabilities, right? Let's actually just append to that. So to compute the probability, we are going to be plugging each of the samples into the simulation, the crash. So let's just make sure our simulation actually supports a vector of inputs. So the result is also going to be coming out of as a vector. So our result is going to be crashed with a delta V and T. So if we run this, we are going to get a result that's also going to be a bunch of zeros and ones, right? Well, in this case, looks like everything is a 1, so we probably need to increase our initial distance. So if we take the mean of the result, it's going to be essentially what's the proportion of the result that are 1, right? So we see a 96 probability of crashing, so which is probably too large. So that means we probably want to increase the initial distance from 10 kilometers, for example, to 15 kilometers. So if we do that and we compute the crash probability again, probability is going to be equal to mean of result, right? We have decreased our crashing probability to 88%. So that probably means we still want to increase it further. Let's say 25 kilometers. We do it again. We have decreased our probability to 71%. And as you can see, like let's decrease it further to 100 kilometers. And then, well, we get a probability of 0, right? That means we can probably safely decrease our distance to 80 kilometers and try again. Say that, and right, then our crashing probability is 1.2%. And you can, this is now a simulation you can play with to figure out what is going to be a acceptable distance, right, over which you can still safely mine the asteroid without having to decelerate too far away and spend too much time during the deceleration, right? So we have walked through a computation example of how to treat a probabilistic input in a very simple simulation and figure out what is the probability of some kind of undesirable outcome. And first of all, any questions on this procedure, on the example we have went through?